Molecular structure. Covalent bonding is when two or more atoms share electrons in their outer shell. All organic compounds are held together by covalent bonding. Covalent bonds are very strong because of the sharing of their electrons. Ionic bonds are formed when one atom gives up an electron to another atom of a different material. This makes the first atom positively charged and the second negatively charged, and that causes them to attract to each other, forming a new substance. Metallic bonds are metallic atoms that give up their electrons in their outer shells to form a common pool of electrons. This pool is called an electron cloud. The electrons are free to move around and in between the atoms. Elements. Any substance that contains only one kind of an atom is known as an element. Because atoms cannot be created or destroyed in a chemical reaction, elements such as phosphorus or sulfur cannot be broken down into simpler substance by these reactions. An example, water decomposes into a mixture of hydrogen and oxygen when an electrical current is passed through the liquid. Hydrogen and oxygen, on the other hand, cannot be decomposed into simpler substances. They are therefore the elementary or simplest chemical substances, which means they are elements. Each element is represented by a unique symbol. The notation for each element can be found on the periodic table of elements. The elements can be divided into three categories that have characteristic properties: metals, nonmetals, and semimetals. Most elements are metals, which are found on the left and towards the bottom of the periodic table. The semimetals can be found along the dividing line between the metals and the nonmetals. And here is the periodic table, and if you notice, it's composed of mostly metals. And this is in your textbook also. Molecules and compounds. Now, a molecule is formed when two or more atoms join together chemically. A compound is a molecule that contains at least two different elements. All compounds are molecules, but not all molecules are compounds. Elements that make up an oxygen molecule and a water molecule. Compounds. Elements combine to form chemical compounds that are divided into two categories. Metals often react with nonmetals to form ionic compounds. These compounds are composed of positive and negative ions formed by adding or subtracting electrons from neutral atoms and molecules. Nonmetals combine with each other to form covalent compounds, which exist as neutral molecules. The shorthand notation for a compound describes the number of atoms of each element, which is indicated by a subscript written after the symbol for the element. By convention, no subscript is written when a molecule contains only one atom of an element. Thus, water is H2O and carbon dioxide is CO2. Grains and crystals. Large groups of atoms or molecules that form together, ice crystals, minerals. They are oriented in a neat, orderly formation, which form geometric shapes. The grain size and structure influences a metal's characteristics. Metallic grain formations. Through the process of heating and cooling, grain structure can be manipulated to achieve desired properties for manufacturing. And as you look in step 1, molten iron, far above the upper transformation temperature. It's a liquid form, which steel, iron melts between 25 and 2700 degrees Fahrenheit. As molten cools, slowly the first unit cell solidifies. In step 2, you can see that. And then branches develop as the iron continues to cool. As the metal continues to cool, several colonies, and these are called dendrites, start to form. As solidification nears completion, boundaries contact each other. And then when it's completely cooled, the iron has many grains. And here's a crystal lattice with planes of atoms. We're going to talk about lattices here in a second. Structures of metals. Lattices arrange themselves in a uniform structure and repeat themselves throughout the material, and they're aligned on parallel planes which form the grain structure. Here's metallic crystalline structures. Bodied-centered cubic, face-centered cubic, and hexagonal close-packed structure, depending on what the material is, whether it's steels, aluminums, and we'll talk about each one of these materials and which structures are in them. Here's a bodied-centered cubic lattice. Examples of these, so you can see it has an atom in each one of the corners and one right in the center. Examples include chromium, iron and steel, molybdenum, tungsten, vanadium. It is brittle with very high melting points. Face-centered cubic lattice. Face-centered cubic lattice is ductile and easily formed. Examples of materials that contain face-centered cubic lattice is aluminum, copper, gold, lead, nickel, platinum, silver, and we'll talk a little bit more about face-centered and bodied-centered and how metals is one of the few materials that transforms itself. Hexagonal close-packed lattice. That's when it is heated, it has a coarse grain structure, can become brittle and lose toughness. Examples are cadmium, magnesium, titanium, and zinc. Allotropics. The most common is iron. When it is heated, it turns to a face-centered lattice structure. And then when it's cooled, it reverts back to a bodied-centered lattice. So it contains two different lattice forms. Shape memory metals. These are kind of cool. Nitinol. Nitinol gets its name from nickel, titanium, and it was developed by the Naval Ordnance Laboratory, NOL, in the 60s. So it's been around a long time. So it was nickel, Ni, titanium, Ti, Naval Ordnance Laboratory, NOL, therefore the name nitinol. Flexium is a material that can retain its original geometry when reheated. Think of a car that's been damaged, and then you take it through a hot car wash and it returns to its original shape. Flexium is also designed in the use of eyewear because nickel was known to cause skin irritations. So these materials can be bent, pulled, moved, apply heat to them, and they retain their original geometry. Kind of cool stuff. Mixtures versus compounds. The law of constant composition states that the ratio by mass of the elements in a chemical compound is always the same, regardless of the source of the compound. The law of constant composition can be used to distinguish between compounds and mixtures of elements. Compounds have a constant composition, mixtures do not. Water is always 88.8% oxygen and 11.2% hydrogen by weight, regardless of its source. Brass is an example of a mixture of two elements, copper and zinc. It can contain as little as 10% or as much as 45% zinc. Another difference between compounds and mixtures of elements is the ease with which the elements can be separated. Mixtures, such as the atmosphere, contain two or more substances that are relatively easy to separate. The individual components of a mixture can be physically separated from each other. Chemical compounds are very different from mixtures. The elements in a chemical compound can only be separated by destroying the compound. Example, a mix of people, or a group of persons is easy to separate. But to separate a person, as in limb from limb, would kill them. Some of the differences between chemical compounds and mixtures of elements are illustrated by using the following examples of Raisin Bran and Crispix, those two cereals. Raisin Bran has the following properties of a mixture. The cereal does not have constant composition. The ratio of the raisins to the bran flakes changes from sample to sample. It is easy to physically separate the two elements. Ergo, you can pick out the raisins and then eat them separately. Crispix has some of the characteristic properties of a compound. The ratio of the rice flakes to the corn flakes is constant. It is 1:1 in every sample. There is no way to separate the elements without breaking the bonds that hold them together. Solutions. Solutions are a special kind of mixture. One substance is thoroughly dissolved in another. One of the materials is the dictator, and the other is the submissive. The dictator is known as the solvent, and the dissolved material is the solute. Let's see. Solutions are homogeneous mixtures, which means they are not chemically bonded together, but they attract to each other. That makes the solution the same throughout. So, common solutions that we see every day, maybe every day, depending on where you're at. You go to the ocean, salt water. Salt water is a solution of salt and water. Sugar water, such as Kool-Aid, soda, mouthwash, etc. Many common use things are solutions, where something is dissolved in the other. A solute, such as sugar or salt, dissolved in a solvent, such as water. So again, you see the differences. Which one is the solute? Which one's the solvent? And usually the solvent has more quantity than the solute. So there's going to be more water in salt water than there is salt. Now let's talk a little bit about solid solutions. Solid solutions, the dissolving action takes place at high temperatures, when both solids melt and become liquid. Iron and copper are the most common solvents. Alloys and metals is a good example. We'll talk a little bit about alloys here now. Alloys. Two or more metals are dissolved together in a solid solution. Steel is an alloy of iron and carbon. Bronze is an alloy of copper and tin. Brass is copper and zinc, and so on and so forth. There's thousands, if not hundreds of thousands of alloys. The metals that are dissolved, the solutes, are also called alloying elements. So we take those alloying elements and we want those characteristics of the materials that we're adding to the solvent. Metallurgical and chemical terminology. Things that we talked about during this lecture. Atoms, elements, molecules, grains and crystals, compounds, mixtures, solutions, solid solutions. And last but not least, alloys. And the information that I've got for this or from your book. And from this website, and this one also.